Are you there, Dale?
I said you don't have that much
What?
time.
Does the camera look okay?
I don't even know what problem is.
Looks good.
You can see Sammy over there?
Huh?
You can see Sammy?
I can see Sammy, yeah.
Okay.
And I can see Chloe.
Okay.
I feel so special that they have our names memorized. I know. I'm gonna go home and cry and study. They need to make, if they're gonna charge this much for college textbooks, they better be tear-proof. I just need to say that.
Do you feel a little bit better?
I feel better about the chain rule. Overall with the past test scores, I feel generally unprepared for a test, no matter how much I study. But I'm more worried about my chemistry exam tomorrow. Because I didn't understand a word he said in class yesterday. And he's like, and problems like this are going to be on the exam. I was like, problems like what? And we don't have the benefit of being able to go look at the videos of class. What's done is done. And I need to meet with Ms. Holmes so I can sign up for humanities. Like, continue ed class. Fun stuff.
Oh, for the trip?
I'm so excited.
Hey, Dale.
Yes.
We really need to have a discussion about spring.
About spring?
Yes.
That's okay.
Mainly because our spring breaks don't line up like they did for fall break.
Oh.
And I'll be in Ireland for all of spring break.
And I'll be in Costa Rica.
Costa Rica. Well, maybe I can get permission from our dean to make our students come on spring break, and we can take spring break a different week or something. I don't know. So yeah, can I call you after class?
Sure.
I've got the contract ready to send out, so we're gonna.
All right, that's why we need to talk and figure out what's going on. So,
And
I have a class at 9:30 come in, so I can try to catch you with that, but
I have class at 10:15, but I'm finished at 11:30. So if you want to call around.
11:30?
Yeah.
Okay, so if I don't get you right after this class, then I'll call you at 11:30.
Okay.
Or yeah.
I'm going to get the email out this afternoon, the current, most recent draft of the ISA.
Do something with your hair.
I spoke with Jory, and we're going to hold off on the, I'm going to break that into control, into the
Yeah, I
contract.
think I do.
You got the basics done, Mason?
Do you ever make any progress in doing that?
When you left us.
The chin, this month, they got form, and once we got the form,
Has he put the grades in for our
it's fine. If they want.
I think he has. Because he has the grades and the extra credit thing. Well, no. I guess it's 2 sets of extra credit.
Little more.
efficiently and expecting my grade to go up substantially.
Somebody watch the board again?
I was just thinking wax on, wax on. Wax on,
Oh,
wax on. Yeah. No, I don't know what happened. It's this sideboard flat. The middle board's got more slack. I don't know what wrong with the Excel graph. It's an Allen wrench. And a screw wrench on the bottom.
Don't you like taking this off, or am I too comfy in this? That's a real question.
Yeah, I normally carry them around with me. Yeah, it's not in my back pocket. It might be.
That's so awesome.
I thought you were styling.
Right. What happens if they didn't film it and they gotta redo it again? More cars are registered in New York. I thought they always did special effects for things like that. But apparently,
See, you thought you were styling, but you just didn't end up being Randy.
that is so
Oh, wait.
I don't know.
You'll wake up one day and you're 40 and you'll realize you're just Randy Stanley. That's his dad. And you'll just see yourself.
Do you look like your mom or your dad?
People say I look like my mom. Yeah, I mean, he has some of the facial features of his mom, but he has like the father physique.
In the next chapter, we're learning
The dad's
application.
Yeah, we're Brenda.
fun.
Newfoundland?
So his friend and his
I
friend's
read that
friend,
chapter
but
because there were
my
some people
friend
saying,
made a point
when
not
are we
to
ever
mention my
going to
dad's
use
name.
this?
Yeah.
He also must have
Even
joined
though it
Kid
probably
Rock
won't
back in the
experience.
90s.
Who's Kid Rock?
Kid Rock?
Who's that again? Kid Rock?
It's almost time. I'm going to get started.
Okay,
First off, I don't have your rework graded. I was out of town all day yesterday at a conference. By the time I got home, I drive home for 2 hours or so through traffic. I didn't feel like that's why I didn't do it. So I'll try to get that back to you tomorrow. The drug test tomorrow. In the meantime, questions on homework is the order of business now. So let's see where we are in terms of homework. Last time we did 1 or 2 problems from section 2.4, so I'll leave it open to that. And what I'll do is just write down a few numbers of the problems y'all want to talk about. So let's start with section 2.4. Does anybody have 1 or 2 last questions on 2.4? They're having trouble that they're going to go over. And we got to get to 2.5 and 2.6. 2.4 first. Any questions? Elise?
47. 47.
47. And we've got 4, 47, 51. Okay, so let's take a look at number 47 and 2.4. Okay. Second derivative, that's what that stands for. 47. Second derivative with respect to x of x times the square root of 1 all to the -2. Okay. First of all, we realize that this notation here means second derivative. So that means we're doing the derivative of this stuff. So I'm going to rewrite this stuff algebraically. So this would be, first of all, recognize that the square root of x plus 1 is x plus 1 to the 1/2 power. So if I apply my power, exponent rules from algebra on these 2 factors, I can get x to the -2 times, and this will become x plus 1 to the -1.
You know, I don't get it.
Yes?
No, I don't get it.
You know, okay.
Okay.
Question, Rizzo?
What happened to the 1/2?
Real darn good question. What happened to the 1/2? So I'll explain to Rizzo what happened to the 1/2. I had a power of -2 on the power of 1/2. Rules of exponents.
Are you just multiplying them?
Yeah.
Why are we skipping steps, Daniel? This is all I get so wrong.
Okay. Again, this is not the only way to do the problem. You could leave it as a radical. You could do all kinds of things differently. I think this might be the easier method. What is this? How can this be rewritten?
As a product rule.
Before I start doing derivatives, I can do a lot of things. Let's say I want to make it as simple as possible algebraically so that my derivative process is easy. Does that make sense? So this could become 1 over x cubed plus x squared. How did I do that? Yeah, well, I got an x squared that goes in the denominator. I got an x plus 1 that goes in the denominator, and then I distribute. I'm thinking ahead. It might, if I leave it like that, what derivative rule am I going to have to use if I leave it like that? Do I want to do the first rule? Maybe not. How else can I rewrite it? That's how I could have rewritten it this way. I'm just, again, there's not one way. There's lots of ways to handle it, but I'm trying to get my algebra out of the way as much as possible so that when it's time to do the actual derivative work, that's as easy as possible. Now I've got this simplified down to, that looks pretty easy to me. That's just a simple polynomial raised to -1. That's a simple chain. So that's okay. So I just have to do the derivative twice. I'll do it in steps. So working from the inside, I got a derivative of this, and after that I got to do a derivative again. So the outer derivative hasn't been done, but I'm going to do the inner derivative. The inner derivative right here, I got a power rule on the outside and then a chain rule. So it's going to be -1 x cubed plus x squared to the -2 times, and now I got to do the chain rule derivative of that inside stuff there. So that's 3x squared plus 2x. Again, this part right here was the chain rule.
Can you move it over to the side a little, please?
You see that now? So I did a chain rule on the inside of this function. Can we all see this? Now I still need to do one more derivative. So it said to do the second derivative. I've only done one derivative. But before I do that, I stop and think again. I could just jump in and start going. What's that going to entail if I do that? If I just kind of jump in and start going, well, it's going to be a product rule, and inside the product rule is going to be a chain rule. That might be the easiest way to go. It might not. I don't know. Well, how else can I rewrite it if I wanted to rewrite it? Just instead of doing, let's write it as, this time I'm going to do it as a quotient just to say I can. Okay, so what does this become as a quotient? So this becomes negative 3x squared plus 2x over x cubed plus x squared squared. Okay. Again, I could have stayed with a product rule and chain rule inside the product. Now I'm going to have a quotient rule with a chain rule inside the quotient. That could be a whole lot easier. It's just a different way of looking at it. Whatever. Different ways. So now let's review. How do I do the quotient? What does that entail? I have to do the derivative of the numerator. Okay, so derivative of negative of 3x squared plus 2x times the denominator minus the numerator, which is a minus itself. So I'm actually going to go ahead and make it a plus 3x squared plus 2x times the derivative of the denominator all divided by the denominator squared. So that becomes x cubed plus x squared to the fourth power. last step is to do the derivative of these two pieces right here. This numerator and that denominator have to still be differentiated. Numerator part, I have a negative multiplier, but that's just a constant -1 multiplier, so I can come out in front of the derivative. And then I just have to do the derivative inside, which is fairly simple. That's just 6x plus 2. Plus, and then derivative of the denominator. Now that's going to be a chain rule because I have a power on the outside. So it's going to be 2 times x cubed plus x squared, 1 power, times 3x squared plus 2x. And all that is over plus x squared to the 4th. And I mean, you could probably clean it up a little bit somehow. Pardon me? Well, I could distribute the negative sign, but I probably honestly wouldn't. What I could do is I see an x squared plus, excuse me, 3x squared plus 2x multiply together, so I can make that a square of that. It's like I have a square of this right here. I can rewrite it in a couple different ways. I don't know exactly how the book has the final answer written. But I finished doing all the derivatives. I'm just now doing a little bit of algebra cleanup. Say I'll pull that 2 in front and make it 2 times x cubed plus x squared times 3x squared plus 2x squared over plus x squared. Follow that? Elise, I think you asked the question. Did that answer your question?
Yeah.
Okay. Number 51, real quick. Oh my gosh, the third derivative. Okay. All right. So the third derivative, x of x times 3x squared plus 1 to the 9th power, evaluated at x equals 0. Okay. Well, so we got two things we're going to do. First of all, we're going to find the third derivative. That's what this means, the third derivative. And then when we're done finding the third derivative, the last thing we have to do is this, which says to evaluate at x equals 0. So I got 2 things I got to do on this problem. Okay, so let's start off with I got to do derivative of x times 3x squared plus 1, 9. And eventually that's got to be evaluated at x equals 0. Okay, so yes, the chain rule will be involved. You're right. But what will the first rule be that I have to apply? I have to do a product rule. It's a product. I would do a product rule, and within the product, I have to do the chain rule. So you're right there. So this is equal to the derivative of the derivative of. Now, when I do the derivative of this stuff for the first time, I have a product. Well, I have to do the product rule. So I have to do the derivative of the first, which is a 1. It's 1 times 3x squared plus 1 to the 9, plus the first times the derivative of the second. Well, that's going to be a chain rule, so 9 times 3x squared plus 1 to the 8th power times, and then I've got to do the derivative of the inside with the chain rule. That's going to become a 6x. So we again how that happened. The reason I've got a plus sign right there is because I did a product. That product right there. The reason I have this time sign right there, that's because I have a chain rule of inside function and outside function. Now, before I try to do the next derivative, I'm going to clean this up a little bit, if I can. Try algebraically. I really can't clean that up in here. That's just 3x squared plus 1 to the 9. This becomes 6x squared times, oh, not 6, 9 times 6 is 54. 54x squared times 3x squared plus 1 to the 8th power. I gotta do the derivative again. Okay, so let's see. I got a chain rule in this first one. That's just 9 times 3x squared plus 1 to the 8th times, chain rule, 6x, plus, now what do I have to do for the second part of this derivative?
What is it,
I've
product
got a
rule?
product rule involved, and then part of it is to involve another chain. The product rule, derivative of the first. 2 times 54 is 108 times x times the second without a derivative, plus first without derivative times, and then I can do the derivative of that thing. So that's going to involve a chain rule because I've got an inside function and an outside function. So I got 8 times 3x squared plus 1, 7, times, chain rule is 6x.
I love it.
Well, before I try to do the next derivative, I'm going to see if I can clean that up a little bit. So coming up over here, so I guess we have to pan the camera a little bit. I see a 54x times parentheses to the 8th, and then I've got 108x times the same parentheses to the 8th. So 54 and 108 is 162x. So I got 162x times 3x squared plus 1 to the 8th power. And here I've got 6 times 8 times 54 times x cubed. So whatever 48 times 54 is, 4 times 50 is 100, 8, 40 times, that's 2,000. I don't want to take a time on it. 2,592. So plus 2,592 x cubed times 3x squared plus 1 to the 7th power. Evaluated at x equals 0. Now you do another derivative. Oh my gosh, how do you think we're going to do that? Same thing, right? We're going to have a product rule with a chain rule, and another product rule with a chain rule. So it's going to get messy. But it's not hard, it's just keeping up with all the pieces. Okay, product rule, let's see. So this is 162. So I'm seeing a product right there. And the derivative of the first part is derivative of 162x, just 162, times the second part without a derivative, plus, then I can do the first part times the derivative of the second, which is a chain rule, 8 times 3x squared plus 1 to the 7th, times 6x, plus, so this plus I just wrote, this plus is that plus right there. This plus came from a product rule. Now I get another product rule I got to get involved in. So I'm going to kind of wrap around. Let's see. So 3 times 2,592 is 6,000, 7,500, 7,776 x squared times 3x squared plus 1 to the 7th plus, I've got another product rule. I got a product right there. Derivative of the first part times the second plus the first part, 2592x cubed, times the derivative of the second part. That's a chain rule, 7 times 3x squared plus 1 to the 6th times 6x. All of that has to be evaluated at x equals 0. Now, at this stage, I could clean that up algebraically if I want, and normally I would want to. Well, why this time do I not really care if I clean it up or not? So I'm evaluating at x equals 0, so just plug in x equals 0, figure out what the number is, and you're done with this one. Let's see, let's plug in a 0. So evaluating at x equals 0, so that's 0 there, so that's 1 to the 8th times 162. So it looks like I've got 162 there. And here I've got a 0 times a bunch of stuff, which is just 0. Here I got a 0 squared times a bunch of stuff, which looks like another 0. Here I got a 0 cubed times a bunch of stuff. That looks like another 0. So apparently the answer is 162 is what I...
Wait,
that's not
in the
right.
first parentheses, when you plug in 0, you get 1 to the 7th power. Wouldn't that just be 1?
Yeah, well,
1 times 8 is 8, so...
But then in this one you have, in the second
Oh, there's 6x
part,
too.
it's 162x times 8 times 3x squared plus 1 to the 7th. So if you put in 0, it's 1 times 8.
times
Oh, yeah,
162
this is
times 0, which is 0.
Oh, that's true.
I'll see it, bro.
I don't know what the book has. I get 162, but maybe let's check it one more time. So if I did all my derivatives correct, so I hope I did, then plugging in 0, so this is my entire expression from here to there, plugging in 0 for x. In this first term, 0 makes a 0 there, plus 1 is 1, 1 to the 8th is still 1, times 162 is 162. But in all of the other terms, there is at least one factor of 0 in every one of the other terms. So here I'm multiplying by a 0 times a bunch of stuff. I don't care what the rest of it is. Once I multiply by 0, it's 0. This term here, I don't care what goes on here because I'm multiplying by 0, so it's 0. I've got a bunch of stuff, but I'm multiplying by 0 there or by 0 there, whatever you want to say, it's still 0. So I get 162. Okay? What's the book say? I hope we're right. I feel pretty good about our derivative. I don't know. 162. Oh yeah. Okay. Now that was 2.4. I think we need to move on now because those are a couple two big heavy-duty problems. We had to practice on some of the other problems in 2.5. So Let's go to 2.5 next. I'm going to go back over here and start over and erase this. Now on 2.5, and again, we want to try to do 3 or 4, maybe 3 problems or something, and then try to get a couple problems from section 2.6 as well.
I need to just learn for myself.
So we're at 2.5. We have a problem we want to discuss. I heard a 35. Anybody else? Davison, you have a problem or two? While you're thinking, I'll go ahead and start on 35, and then we'll see how we're doing. There is something in section 2.5 that we did not do an example of. They call it logarithmic differentiation. I hope you've studied the examples of that, but if not, we need to do one because that's something a little different also. You said number 35. X squared times log base 2 of x times 2.
I can't even see it.
Log base 2 x times 2.
This is called f of x, or do they just have derivative of it? It's called f of x. I assume we're trying to find f prime of x. So to find the derivative of this function, we have to do the derivative of it. Okay, good. You know what I'm going to do before I start jumping on the derivative? I'm going to think ahead. If I try to do the derivative of this as it's written, you're going to have to do a product rule here, and then you're going to have to do a derivative of a log, which we went over that. And then you got to do, inside that, a product rule again. It's going to be messy. But do you see any algebra that maybe I could simplify this function algebraically first before I do the derivatives? For example, properties of logarithms. Properties of logarithms give the logarithm of a product, what happens?
Thank you.
Yeah, properties of logarithms give me that. What's another property of logarithms I can apply as well?
X. Or is it not?
Log base 2 is a inverse function of exponential 2 to the x. They're inverses. So this function here, this expression, is simply x. They are inverses of each other. Okay. So now I'm trying to find this derivative, which I'm going to rewrite as squared times log base 2 of x plus x cubed. That looks like a much simpler problem to deal with than what I had before in my mind.
I can't
Why
even
is
see
it
it.
cubed?
I can't even see it.
Oh, that
Why is it?
question?
Why is the x cubed at the end?
Because I distributed this x squared into this parentheses.
Okay.
Well, x squared times this log, and then x squared times that x makes a x cubed. Now I'm going to do the derivative of that. So derivative of x squared log base 2 of x plus x cubed. So I'm going to split my derivative across this sum, clearly. Which, this is easy, that's 3x squared. How do I do the derivative of this stuff right here? That's the other question. Radical, that's right. So, this time, just to emphasize it, you know, I'll actually write the steps out. So, after the derivative of x squared times log base 2 of x plus x squared times the derivative of log base 2 of x plus, and then the derivative of x cubed. So applying my general function rules of sum and product, I get to here. This was just sum and product. And those general function rules are the ones you use first, generally speaking, because that splits up the derivative into smaller chunks. You know, we call it atomizing the derivatives. So we atomize the derivatives into little pieces. Now we're going to go in and apply specific function rules to the little pieces and see what we get. Okay, so what's the derivative of x squared?
2x.
Log base 2 of x. Plus x squared times, what's the derivative of log base 2 of x? 1 over x times natural log of 2. I would probably clean that up at least a little bit. This middle fraction here has an x in the numerator and x in the denominator, so they would cancel one another. So I would probably say something like 2x log base 2 of x plus x over the natural log of 2 plus 3x. Okay. Problem number 35 in section 2.5. Does someone think of another problem they'd like to look at? 41. Plan of natural. Ooh, 45. Let's see that there. Piecewise. Before I get to piecewise, let's see. 41 x squared ln of ln of x. Okay, let's try that one. Okay, so this is 41, which is f of x equals x squared times natural log of x. Is that right? Did I read that right? Okay. So f prime is going to be derivative of that. So what is the first property you're going to apply on this? Product rule is right. So I'll show that again in steps. So I'll get the derivative of the first times the second plus the first times the derivative of the second. So 2x times the natural log of the natural log of x plus x squared times now So the first part was easy. The second part, derivative of the natural log of the natural log of x. Chain rule. With derivatives, work from the outside in. So the first thing I'm going to do is this is my outer function, and this is my inner. So the derivative of the outer function, keeping the inner function constant, is the derivative of that natural log right there, which is just 1 over whatever's inside, which is natural log of x. But then you have to do the times of, so I'll write it out as another step this time. The derivative of the inside. So again, what's my red? Here's my inner. See that same inner right here and right here. I now have to do the derivative of that inner. So this is 2x natural log of x plus x squared times 1 over natural log of x times the derivative of natural log of x is just 1 over x. I can simplify these x's cancel, so I can get 2x natural log of x plus x over natural log. Now, before we do these slides, we need to talk about this logarithmic differentiation. I haven't asked about yet. It's in this section. And let me go to with you. So the book mentions logarithmic. They don't say, but I'm going to add by using implicit. What does that mean? The idea is if you apply a logarithm to an equation on both sides of the equation, you can then simplify the equation using properties of logarithms and then apply an implicit differentiation to it. Now, there are some instances where using this technique will make your derivative simpler, but not required. There are other cases it's the only way to do it. Okay? So, an example where it might make your life easier, but not required, real quick. Let's suppose y equals x plus 1 squared times x minus 3 over x plus. So there's my function y. I'm supposed to find the derivative. Now, hopefully you see if I was going to go straight at it with the derivative, what would it entail? What properties, rules would I have to use? First rule is the quotient. Second rule is going to be product and chain rule. So you're going to have all of that going on. Okay, great. You ought to be able to do that. But here's a technique that could make it a little bit simpler. What if I apply the logarithm to both sides of this equation? Well, thing is, logarithm of y can't be simplified, but by properties of logarithms, you should be able to simplify the right-hand side. How does it simplify? By properties of logarithms. Yeah. Logarithm of the numerator minus the logarithm of the denominator. And in the numerator, you got a product, so it's the logarithm of this plus the logarithm of that minus the logarithm of this. So this becomes logarithm of x plus 1 squared plus the logarithm of x minus 3 minus the logarithm of x plus 4. So far, so good? That's just basic properties of logarithms from pre-calculus algebra. There's one other property of logarithm that you could use. This square power here, what could you do with it? That can become a multiplier in front of my logarithm. Now, folks, at that stage, it's easy to do the derivative. I'm going to do the derivative on both sides of the equation implicit. Okay? Are you with me? So all I'm doing now, to save writing some little bit of writing space, I'm just simply going to do the derivative with respect to x of both sides of this equation. This is where it's it becomes a shortcut. If you know your properties of logarithms, it's a real shortcut. If you don't, forget it. Just go back to the other one. Derivative of logarithm of y. 1 over y. But because it's derivative with respect to x, you got to do the chain rule. So it's going to be times dy by dx. That's where the implicit differentiation comes in.
Mm-hmm.
Now, how about derivative of 2 times natural log of x plus 1?
2 over x plus 1.
2 over x plus 1 times, but be careful now, folks, be careful. I'm going to emphasize this, times 1. Why did I write that as emphasis? Because it's a chain rule. You got to do the derivative of the inside. Now, the derivative of the inside happens to be 1. But if that hadn't been x plus 1, let's go back and change it. Let's change the next one. Let's make this a 2x minus 3. Let's make that 2x minus 3. So, as emphasis, on this next one, it's going to be 1 over 2x minus 3. Because the derivative of natural log is just 1 over, but I have to do the chain rule, so the derivative of the inside is just 2. Last one is going to be 1 over x plus 4 times 1. Again, because it's not simply x, I've got to keep remembering the chain rule every time. From here, it's easy, folks. I'm almost done. I'm trying to find dy by dx. How do I do that? I got to multiply both sides by y. Is that not what you do? Multiply both sides by y? But what is y? Y is defined way up here. So I'm going to multiply both sides of the equation by y, which is that. So I have x plus 1 squared times x minus 3 over
Minus 3.
minus 3, 2x minus 3, thank you. This is an x plus 4, and then times all of this stuff that I've just created, which I'll simplify as I write it. So 2 over x plus 1 plus 2 over 2x minus 3 minus 1 over x plus 4. So now I'm completed with my derivative. And that was, if you get used to doing logarithmic differentiation, something like that, that's far easier than doing the quotient rule and the product rule and all that stuff combined. But you have to be comfortable with the properties of logarithms. But that's just a case where it can be shorter somewhat than doing the full process. But what about cases where it's required? Move over to this. A fairly simple, innocuous-looking function, x to the sine of x, y equals x to the sine of x. The problem is, how do you find the derivative? If it was x to the square, then it would be easy. Your derivative is 2x. If it was a base like 2, a fixed base like 2 to the sine of x, you've got a rule for that. You've got a rule for x to the n. I can handle that. I've got a rule for n to the x or n to the sine of x. I can handle that. But I've got x raised to something involving x. I don't have a rule for that. Don't have a rule. The answer is not x to the sine of x minus 1. That's not it. So how do we do it? We're going to use logarithmic differentiation. Logarithm of y equals logarithm of x to the sine of x. Before I actually do the derivative, I'm going to simplify the logarithmic expressions as much as possible. So on the right-hand side, what do you get when you simplify? Where did you have it, I think?
Sine of x times natural.
Sine of x times logarithm of x, right? Now I can do my derivative. So I'm going to apply the derivative to both sides of this equation. Derivative with respect to x of log y. Derivative with respect to x of sine of x times log of x. Okay, so the derivative with respect to x of log y is 1 over y
Times dy.
dy by dx, because you got a chain rule involved in the implicit differentiation, equals, now what do I have to do for this derivative? Product rule. I got to do a derivative of sine. What's the derivative of sine of x? Cosine of x times the log of x, plus, then the sine of x times the derivative of log of x, 1 over x. I'm not quite done because this needs to be solved for dy by dx. So let's solve it. dy by dx. I got to multiply both sides by y, but y is up here defined for me, so that's x to the sine of x times cosine of x log of x plus sine of x over x. That's an instance where you have to use logarithmic differentiation, because we don't have a rule that handles a variable base to a variable exponent. We can handle already with the rules we have, if you have a fixed base with a variable exponent or a variable base with a fixed exponent. Not when they're both variable. Logarithmic is now required. Are we clear on that? Okay, other questions that you might have in 2. Let's move to 2.6 real quick while we still got a few minutes, and we'll come back to some others if you want to. So let's cover a couple of 2.6 as well. I have questions. Jake, question.
On your chain rules out there on the LN, do out there. Like the 2 LN times, of x plus 1.
Is this one right here?
Yeah.
Well, this 2 came from, so technically it's that, but there's a 2 multiplier in front like that.
Okay.
Because that 2 constant multiplier.
Okay.
The derivative of natural log of 1 of x plus 1 is 1 over x plus 1.
By definition.
By definition, natural log derivative. But that's not the simple x, so the chain rule yields a 1 multiplier from the chain rule.
You do the derivative x plus 1 to give you 1. Okay.
Yeah. Like over here, derivative of natural log is 1 over the stuff, but the derivative of this inside stuff, chain rule, is a 2. So I mean, I could have made it a 2x, I mean, like, for example, what if this had been x squared plus 4 right there? Let's just pretend. So this would be x squared plus 4 there. So then you'd have 1 over x squared plus 4 there times 2x right there. You see that? So chain rule has to be employed. That's the reason I wrote that 1 in there, was to emphasize it happened to be 1 this time. If you forget it and it's not a 1, then you're going to get it wrong. So be careful. Section 2.6, anybody? Question? At least you had a question. It looked like 4.
30.
30? 30? Is 30 assigned?
No, it wasn't. I was wondering if we could work through it, because it kind of employs a lot of what we're...
I'll work through that. Okay. Well, number 30, as a quick glance, before I ever start on a derivative on number 30, what's an observation you can make about number 30 to simplify it before we start trying to do derivatives?
There's a 1 on the bottom.
Number 1.
What's sine squared plus cosine squared? Just a 1. So the denominator is gone, it's just a 1. So now you're just doing the derivative of log base 3 of 3 to the x, which is just x. So f of x is just x. The derivative is just 1. Does that make sense, at least?
Yeah.
The properties of trig properties gives me a 1 in the denominator. Cosine squared plus sine squared makes a 1. Properties of logarithms, because logarithm is the inverse of exponential, then the numerator just simply becomes an x. So your whole function reduces down to an x, and so the derivative of x is just 1. Other questions in section 2.6? No. Oh my gosh. That one looks like it could be a beast.
I don't even know. We'll see when he writes down the number. He'll probably say it both.
Now we're doing 2.6, number 29. 29 says f of x equals negative 2 to the x over 5x times sine of x. Well, again, when I can, I'm going to simplify my function as much as possible algebraically before I start trying to derivatives. However, this time, there's no real simplification, because I've got an exponential function, I've got a polynomial function, and then I get a trig function. Those don't really mix and match well. So I'm doing a lot of work. What's the first property you're going to apply? Quotient. And so f prime of x is going to be the derivative of the numerator times the denominator minus the numerator, which started negative, so I'm going to make it a plus, times the derivative of the denominator. Now, the derivative of the denominator is going to be that's a product, so I'm going to write it out as the derivative of the first part times the second plus first factor times the derivative of the second factor. All divided by the square of the denominator. Okay, so derivative of negative 2 to the x. Negative 2 to the x times natural log of 2 is correct. The negative sign is a constant multiple, so I can just pull it out in front. The derivative of 2 to the x is an exponential, which the rule is it's just an exponential times log of the base times the derivative of the inside if it's not simply x. And it is simply x, so we're done there. So that gets multiplied by 5x sine of x. Then I've got a 2 to the x there, so let's see. I got derivative of 5x, that's 5. And then I've got a 5x times derivative of sine of x. So what's derivative of sine of x? Cosine of x. Okay, I'm done.
Is that it?
There might be a little bit of cleanup you can do there, but not really a whole lot, so I'm just going to stop there. Another question in section 6? Okay, so we got here, Chloe, what's yours?
I just have a question about the test tomorrow. How far do you want us to simplify our answers?
As much as possible.
Well, if it's some fairly obvious simplification, like on this example here, on the middle board, where I had an x squared and an x in the denominator, and those can cancel fairly simply, then you should probably do that. In terms of the example we just did over there, there's probably a little bit of simplification I could do, but if you can get through on something like that to that stage, we'll call that good. That's not a real precise answer, but mostly I'm looking, can you apply all the properties of derivatives is the main thing I'm looking for. So, Josh, you have questions? Or Bill? Not Josh. Josh has a question.
Yeah. I was wondering if we could do number 9.
I'm sorry, what?
If we could do number 49.
49. Secant of 1 plus inverse tangent of x. Oh my gosh. Boy, you got this. 49. Okay. So if I'm going to do the derivative of this, I have to do derivative of secant of 1 plus inverse tangent of x. Okay, so I'm going to have to do a chain rule. Outer function of this chain is secant. Question is, do you remember what the derivative of secant is now? Secant times tangent is right. Secant times tangent. So I got the secant of what's there times the tangent of what's there times the chain rule, the derivative of what's inside. One more time, this times right here, that times came from the fact that secant, the derivative of secant has a product of 2 things. On the other hand, this times right here came from the fact that you have an inside chain to deal with. Okay, so I still have another derivative I gotta achieve. So this is the secant 1 plus inverse tangent of x times the tangent of 1 plus inverse tangent of x times. Okay, so the derivative of 1 is 0 plus the derivative of inverse tangent of x. Yes. So this is 1 over either x squared plus 1 or 1 plus x squared. I think is how the book writes it, but it doesn't matter. X squared plus 1 and 1 plus x squared are the same thing. And then if, now it's not the case, but if this had not been a simple x, there'd been more to it, you'd have another chain rule. But we'll stop there because it's just a simple x. So technically, again, this was technically a 0 plus, but I didn't want to write the 0 plus because that's just too much effort. So there we go.
Okay.
Okay, Josh, did that answer your question?
Yeah.
What else had another question? 2.6 real quick.
Can you do 39?
39. X squared times arctangent of x squared. Well, first of all, do you know that arctangent is the same thing as inverse tangent? That's good. You know that, then it's easy. Okay. So let me emphasize that to everyone from a reminder from trigonometry. That this notation is equivalent to
Just tell me what you
that
want.
notation.
Tell me just right there. Because I'll do
In some books, they prefer arctan because it's actually more indicative of what's happening. It's telling you that you're finding the arc whose tangent is x. In other books, they prefer the inverse notation because they're indicating that this is an inverse function to the tangent function. However you want to see it, they both give you the same result. So they are equivalent. The derivative of arctangent of x is the same as the derivative of inverse tangent of x. So this one, you have it now, or so you got that. Now you can see it. Jake, another question?
Oh, what definitions do you want first? You know what I'm saying? Like, switch. What should we look at? Yeah.
Which one, proof-wise?
Yeah.
Take a look at it. I think the product rule is a good thing to know how to do. I would say maybe one of your inverse trig rules. How did we do the inverse trig rules? Remember how we proved those? We did implicit by changing the function.
Yeah.
Maybe look at an inverse trig rule as well to prove.
I remember.
Yeah.
I don't think
The question was, are you going to have the power rule proof on there? And I said, probably not. So mostly it's going to be a lot of derivatives, a couple of proofs of the properties, applying your derivatives, finding the equation of tangent line, things like that. As you did on the last test, but what do you realize that we're still doing the same thing?
Yeah.
On the last test, you were using the definition to find the derivative, using limit h goes to 0. You found the derivative, then you found the slope of the tangent, and then you found the equation of the tangent. Well, what are we doing different now? We're not using the definition, we're using all these properties, But you're still finding the derivative, which still tells you what? Slope of the tangent line, right? So you still should be able to do the same problem, but now you don't have to use the definition to find the derivative. Okay? So question?
You wouldn't give us f from x, tell us to solve that.
Yeah, we had some problems like that too, where you had to find the family of antiderivative functions and then find the one function that goes, we're finding the whole family of antiderivatives and then finding weird cousin Henry or whatever that was the one that goes through the single form. I need to look at that as well. And some of the finding antiderivatives can get a little bit messier. Well, some of them are fairly simple. The book has an example, real quickly, of one that might be a little bit more complicated. Rezo has a question. Rezo, you have a question?
What was that family word again? Is it antiderivative family or what was the term?
It's a family of antiderivatives.
Great.
For example, real simple example, if f of x equals 2, excuse me, if f prime of x equals 2x, then f of x must have been an x squared, but there could have been a constant because the derivative of any constant is equal to 0. So I need to remember to put a c on there. This gives me a family of all of the cousins and aunts and uncles. But if I tell you a single point it goes through, then what does that tell me? So if I said whatever, 1, 3. My function has to go through. So how do I figure out what C is? If I know this information, this is a family of parallel curves. Whole family of people who look a lot alike, except for one. Each one is just a little step above the other. So how do I find the one that goes through this point?
You just plug it in?
Yeah.
All right, yes, I'm giving you an x. I'm giving you an f of x. It's easy. So 3 equals 1 squared plus c. Apparently c is equal to 2. So my family is this. This tells me the single member is that.
Okay.
Now the book also does some that are a little more complicated. That was fairly obvious by most of us could do it by quick inspection. But I mean, some of them might. The book has some that are a little more complicated in there that you might want to try. Like, what if f prime of x equals 1 over 1 plus 4x squared? That's a good example of this. So your first guess, if you were to guess and check, it was easy to guess that. But this one's a little less easy. But what does that sort of look like to you? Looks a lot like inverse tangent. So what if I guess f of x is equal to inverse tangent of x? But the derivative of that is 1 over 1 plus x squared. Well, that's not exactly the same. So let's guess again. What if I guess? So I've tried to guess, but that didn't quite work. Let's make another quick guess. How about inverse tangent of 2x? Okay, let's try that. So inverse tangent of 2x, and you're real close. You're going to get f prime is 1 over 1 plus the square of that. So the square of 2x, but times, because that's not simply an x, times the chain rule of 2. But that's real close, folks. That comes out to be 2 over 1 plus 4x squared. This and this are very close. How can I make them be the same? What if I multiply this by a half? Okay, so let's start again. F of x equals 1/2 of the inverse tangent of 2x. Now when you do the derivative, the 1/2 is a constant multiplier. And the derivative of that, we've already seen, is 2 over 1 plus 4x squared. And the 1/2s cancel, so I get 1 over 1 plus 4x squared.
Yeah.
So there's my function that actually works for this one. You just need a plus. Well, plus. Okay. So we have a test tomorrow. Most of it will be a lot of derivatives, and a couple of applications, and a couple of proofs. Ready? No question?
Am I gonna have to figure out how to do piecewise functions on my own?
How to figure out to do piecewise functions. What do you mean how to figure out?
The one we didn't do on 2.5.
Well, we've done derivatives of piecewise functions. How did we do them?
We just did the derivatives of the individual pieces.
Correct. And then you check the boundary point, and if the derivative value at those two boundary points was the same, then good. If it's not, then you put the derivative at that boundary point does not exist. Remember doing that?
Yeah.
So we did that before when we were doing with definitions. And h equals 0. You should be able to do it more simply now because you're doing the same game. You're just using the rules to find the derivatives instead of having to use the definition. I'll get the point that all the applications you've seen plus more that's coming can be done, but just more simply because you don't have to go through that definition every time around. We haven't learned something new other than some shortcuts. We can start early tomorrow, this class. They can start late if they like, or start on time.
Do you want to stay and do piecewise reason?
Yes. Please.
Do you want to do it on the board up there?
Yes.
Sorry about that. I think it's smart. No.
Wait, which board?
A board that isn't a board. Like at all.
Brittany, do you just want me to write a draft of the chemistry essay?
No, so you're not plugging in just X everywhere you see an X.
Do you want to just send me the research and then I'll write the essay?
I'm not gonna do
We
just
should
one
get
time.
together.
You guys
on
write
that.
Actually, it looks like this.
Yeah.
When you plug it in,
You guys write
like,
a
this is
Yeah. Yeah.
the derivative of taking it.
Get on like a Friday.
Just let me do like a.
Just let Rezo do the whole thing.
We're not letting Rezo
I
do.
have to.
We're all getting 5s.
Yeah, dude. Let me pull Thomas Jefferson on this.
Wait, Mark? Huh?
I just don't want to be here, man.
Go home.
I want to go
Don't go
home.
to
We'll do it tomorrow.
We have
It's one of the best
tomorrow.
classes.
Yeah.
I really wish I had dropped out before
Yeah.
it started.
And we can put it
How
on.
is it?
Terrible. We're taking our first test tomorrow.
Alright, you can write this up here if you want.
Okay.
I haven't understood anything since chapter 1. I honestly don't know what he was talking about. And then he was like, you guys need to know how to do this problem and practice it at home. And if you're doing it on the test for the first time, it's 60. And out of 60 questions, like 60 minutes is the time you take 45.
No, we just reviewed avant-garde, the number thing. We just did a bunch of that stuff. That's all we
Avant-garde's
did.
number?
Yeah.
Avogadro.
Avocados. That's all we
Is there
did.
anything?
There was homework due tomorrow, but it is due Tuesday now. And he said it'll take a while, but realistically, we can get it done in like,
I mean, I'm already done with like most of it.
oh, I haven't started.
Why?
It's
I
not on the
forgot
calendar.
calc work, but I did the chemistry
It's
work.
not on the movie calendar though, and he said it was. And,
You know,
like, he said
I
it
don't
was
even
classes.
Hearing and keeping on doing it is productive because my mind just works differently and I just end up more confused the longer I'm here, but I'm forced to come here out of attendance. So, I thought I had it last night, but now I'm confused again, so I'm just gonna have to relearn it.
Okay, so the first thing you're gonna do is take the derivative of that.
Yeah.
So you've got, so you're finding f prime of x, right?
Mm-hmm.
And then you're gonna have three spots that you're looking at. You're gonna look at less than -2, greater than -2, and then what happens at x equals -2.
Okay.
You've got to.
So the derivative of the 2 to the x part is 2 ln of 2 to the x ln of 2. Right, and that would be if x is just less than -2.
Yeah.
And then this could be rewritten as that. 1 over x squared. Is that what it is?
Yeah.
So then the derivative of that is